Okay, so the basic theory that you're dealing with is something called the photoelectric effect. Now, the photoelectric effect theory is the following. Light is actually a particle called a photon, and the size depends on a constant called Planck's constant. You can look that up. And frequency. So the higher the frequency of the electromagnetic light incident, the bigger the photon, right? So something like red. Right, so red is the smallest frequency. So red would be a tiny photon, and red light, and then as you increase that frequency to the blue, the violet, you would have a larger photon. So what happens? These photons fall on the cell, and depending on the size of the photon, the electron receives a certain amount of energy, right? And that amount depends on the calculation of H, Planck's constant, and frequency. So the bigger the frequency, the more kinetic energy the electron has, and that will have an effect on the electric current. Okay, now you would need to look up how having more kinetic energy would affect here the layer within the blah blah blah, producing an electric current. Okay, so basically this electric current, you're saying that is because the holes move in the opposite direction from the electrons. So if the electrons are moving faster, how does that affect the current? Now, if you can't find that, then the next thing I want you to look at is something called the threshold frequency, because every material has a frequency below which it just doesn't work. So it's called the threshold. The threshold frequency is important because if the light that hits the cell or any other material is of a frequency that's not big enough, then you're not going to get a current flowing. So therefore there is a range of frequencies at which a solar cell will work, and some that won't. And I would assume that each material has a different threshold frequency. Now, what that means is that you will only get current being generated at certain frequencies, so therefore the cell is not so useful in the range of frequencies. So I guess the question what you're looking at is, why doesn't a solar cell work at all frequencies? And it must have something to do with this threshold frequency. And if not, you could still use it in your hypothesis. Now, perovskite, I suspect, then, could have a lower threshold frequency. So that means it will work with a bigger range of frequencies. If it's got a lower threshold frequency, that means that it will work with more photon sizes. I don't know, have a look at that. But basically, you need to have something attached to this section which leads into how the current that you eventually generate is frequency dependent. When you've done that, you then need to talk about intensity. Intensity is a little bit easier. Okay, now intensity is the amount of photons. So if you increase the intensity of the sun, that means that you have a very bright day with less clouds. Then you have more photons. So intensity is directly relating to the number of photons. Now, if it's a bright sunny day, you're going to have more photons landing than a day that's cloudy. So therefore, as you've said here, you get more holes, right? So it makes sense. It's easy to understand by creating more holes, you would create more current. Okay, so make this connection, because you haven't done it very well yet, the connection between the holes and the current clear. And then when you talk about intensity, explain how changing the intensity of the light will affect the current. Now, you also need to look at perovskite, right? How would the structure of perovskite affect this relationship between the number of photons and the number of holes? Now, you have a hypothesis in there somewhere. You said that something about perovskite behavior. Is it easier to make holes? I mean, what is it about perovskite that means it reacts differently in brighter light? If you can find something about that, that would be great. But anyway, this entire section has to end like this. It needs to have a big general theory about how cells work, leading to a specific relationship between these holes, electrons moving, and current. And we need some kind of qualitative relationship. If this increases, the current increases. What are the two things that increase the current in a solar cell? And then thirdly, how does frequency and intensity affect the current using the theory base? Okay, I hope that made sense. Okay, now these diagrams about perovskite cells, if you could somehow relate them to that theory that you've just explained, that would be great, because we need to understand, where are the holes here? How do the holes affect the current? Make this relevant in some way to your explanation. Okay, so anyway, now you get your research question and your hypothesis, you can specifically relate this to your previous theory. So you have some substance. Okay, the same with your second hypothesis. Okay, so I know I've already made some comments about this stuff. You do need a lot more theory about what these are for, and then maybe describe what this is. Like, what do these things mean, and why are they relevant to your setup? Okay, now this is super important. You've outlined this independent variable, right? So what you should do now is to fast forward, have a look at your final graphs, right? What you need on your final graphs are, on the y-axis, on the x-axis, sorry, your independent variable. So you should end up with a graph that's power here in suns, and on the y-axis you should have, let's see, for the first experiment, which is the amount of efficiency. That's what you've said, okay? And then secondly, on your second graph, you should have a graph of wavelength, and on the y-axis, efficiency. Now, if you have a look at the final graphs that you've got, you don't have those two. So you either change the variable definition to what you've got on your final graphs, or you make some graphs that look like what you've outlined here. Okay? Now, ultimately, I think this is the big thing that you've got to fix. You've got a lot of data, but you're not interpreting it in the way that you've said you would. So you really need to fix that. Okay, I'm a little bit confused about what this means. Okay, you haven't introduced it. Now these, you had them defined previously, and I can't find them now. I don't know if you've taken them out. Yeah, so let me know what you're going to do with that, because I'm not sure what this is doing. I don't know, let's see the power of one. Some of the power can be adjusted. Yeah, if you are going to use this, please state its purpose and define why we're using these, and the relationship between these two, and how they then relate to your final results. Okay, you definitely need to end your method and label results somewhere. Okay, results. And then start with your tables and then your graphs. Make sure each table has a title and each graph has a title that's clear. Also, make sure that your graphs are big, right? So big graphs, not this. They've got to take up like an entire space like that. Okay, so they're easy to read. So that's the next thing you can do. Okay, so this is where it all goes a bit wrong, right? Now, think about what's your independent variable and what's your dependent variable. Okay, in this data table, you need to link the data that you've measured to your I, V, and dV. Okay, so are you plotting efficiency? Are you plotting maximum power? Which one of these is your dependent variable? And which one is your independent variable? Because if we look at your graphs, they don't relate to your variable introduction. So what you've got to do here is make a decision. Define why. So firstly, explain, because this is the section about process data. Explain what processing has been done. What is the processing? Okay. Why did you work out these things and how? And now, how do they relate to your independent and dependent variables? Now, it could be that what you've said is your independent and your dependent is not what you've actually made or generated. So go back and define it and change it. Okay? But in the end, those two things have to coincide. See, this is a bit confusing now because your maximum power point, so if I look at this graph, irradiance versus maximum power, yeah, this is what you need to explain. Why are you plotting irradiance versus maximum power? Because you haven't explained that fully. You said your independent variable was going to be intensity and the maximum power would be you said efficiency was your dependent variable, right? So go back, have a look at your independent variables and your dependent variable in your explanation. Your independent variable in the end should be on the x-axis and your dependent variable should be on the y-axis. You have outlined your independent variable as intensity and your dependent variable as efficiency, but that's not what we're seeing here. So either go back and explain what your independent variable should be, right? What is maximum power point? Why is that plotted here on the y-axis? Why is this on the x-axis? Or plot another graph of intensity against efficiency. But whichever one you do is fine, but choose one, because at the moment your independent variable is not the same as what you've outlined and what you've introduced, and that's confusing. Okay, so what are you going to do in your conclusion? Okay, so the first thing that you have to do is state the answer to your research question, right? Using data. So state your answer to the research question. Secondly, using the graphs, state any equations that you've generated or state any patterns. Okay, so you should have in terms of your solar cell silicon, right, versus perovskite, silicon versus perovskite with intensity. This is what happens. With frequency, this is what happens. Which one wins? Okay, and your evaluation we'll talk about tomorrow once you've done everything else.